Okay, I think my mic was turned off. You probably can hear me right now. Welcome back. I hope you had a pleasant weekend. So today, ya shabab, we have a very long, demanding lecture. So I'll try my best to cover as much as I wanted for whatever we want to discuss. Okay. So in the last class, if you remember, we talked about, this is just a few minutes revision. We talked about this. We said, okay, that if we have axial loading acting together, and regardless whether we have like torsion, it can be applied as a mean constant value or as an alternating value. Same goes with bending, same goes with axial loading. So the three combinations can be splitted into two equations, the amplitudes all together, which is equation 56, and the means, all of them are together, which is 57. And we said that the correction factor here for including the equivalent factor for including the axial with the bending and the torsion together has been used here through von Mises to get sigma A equivalent or sigma M equivalent. And we said, since von Mises makes the entire state into a uniaxial state comparable to a uniaxial state, then equations like Goodman and Söderberg and Azmi elliptic that uses SE, uses SUT, and use, for example, SY, all of these are going to still be the same. Because remember, when we plug SA prime or SM prime, it is just now comparable to uniaxial state, cyclic state. Or, you know, as per the equation here, we're using one monotonic, which is a static loading, because mean is a static load. And that's why it has been normalized with SUT, while sigma A is alternating, and that's why it has been normalized, divided by an alternating state or a property, which is the endurance limit. Okay, so we had this problem. We said that we have a problem with a mean torque and resulting in a mean torsional stress. We have an alternating torque resulting in an alternating torsional stress, and we have an amplitude bending. That's it. So we said that we can find sigma A prime, sigma M prime, and when we do this, we can also find sigma maximum prime by putting the maximum values inside von Mises. Remember, the maximum values are always the amplitude plus the mean. So I can use the amplitude plus the mean for bending, amplitude plus mean for axial, amplitude, and the mean for torsion, and I get the maximum stresses. And then I plug them into von Mises. Again, and a maximum stress resulting from bending, axial, and torsion all together. So we got that. And then, as usual, we said that if we want to find the yielding factor of safety, then we divide SY by the maximum stress. And if we want to find the fatigue factor of safety, depending on the criterion that we want to use. So if we want to use Goodman, then we use Goodman equation, and this is what we did, and we got a factor of safety of 1.18. And we said also that if you use Gerber and Azmi elliptic, you will get the same one, and we explained that the reason is because this is now Goodman, and this one is the Azmi, and this one is Gerber. And we see that there is a difference here between them. But at this point, they match, their value is the same. So that's why you got the same factor of safety. Now, what do I want you to do is this. What does, يا شباب, أنا بسألكم سؤال. When NF is greater than 1, أنا الآن قاعد أتكلم, this is a question, a general question. Is it only uniaxial loading, a loading which is only bending? Is it only torsion? Is it tension and torsion? Is there a mean stress or there is no mean stress? Is it positive or negative? Regardless, when NF is greater than 1, what does it mean? بشكل عام. Nobody knows.
Can you explain more the question specifically?
When
Regarding
NF, when NF is greater than 1, what does that mean? If you have a client gave you a problem for their machine, you did the calculation, you got NF equals to 1. تروح تدق على الكلاينت تقول له أبشرك NF is greater than 1. يقول لك شنو يعني؟ دافعين لك فلوس احنا تيجي تقول لنا NF، شنو هذا NF؟
The machine will not fail.
What?
The machine or the material will not fail.
Yes. The idea is this. When we use chapter 5, we said that when a factor of safety is greater than 1, what does it mean? For chapter 5, when NY is greater than 1, what does it mean?
You are on the safe side.
What does safe side mean?
No failure will happen.
What does failure mean?
Maybe the material or the specimen can
تنكسر.
maybe it will fail at a some point. It will fail, but a high factor of safety means the material can take.
لا يعني اوكي انت تقول عبد الله قال it will not fail. طيب معناها ان NY when it is less than 1, what does failure mean? تنكسر نصين، يطلع فيها كراك، يتغير لونها. What does that mean?
At the first crack, that means it has failed.
It's a deformation will happen, any type of deformation.
Well, I'm very upset, but doesn't matter. راح التعب يا شباب.
It will yield, doctor.
For chapter 5, we told you, at least for ductile material, our judging point is the yield. The whole equations are around yielding. Now, I ask you a question. When you have a tensile test like this, and this is yielding, شو تقول عن هذا? You cannot call it failure. يعني الfailure هنا is not because it is broken. It doesn't even crack. It's yielding. This stress might be too little. There is a lot afterward. But the idea, you need to understand that failure is decided by us to be yielding for many reasons. I'm not going to repeat chapter 5 again. Now, for yielding failure, I told you this from the beginning, nobody paid attention, is that failure itself, definition of failure is very hard. Some people will think سيارتك لازم تتكسر كلها قطعه قطعه، بعدين جيب السياره ونغيرها لك على التامين ما ادري او على الضمان. You don't have to do this. Maybe your car starts producing noise. You don't need to make an accident because of failure. عشان the agency for the car will replace it for you. So failure is a very flexible definition. You have to understand this. Now, so when n y is less than 1, it means that it's not, you are not good because you will have yielding. يسألك الكلاينت يقول لك شلون يعني؟ تقول له يعني بيصير عندك yielding. انتهينا. Now, when nf is less than 1, it means you will have finite life. مو تتكسر الدنيا. When nf is greater than 1, it means theoretically you have infinite life. It means you are below the endurance limit, below it. Now, when you are below the endurance limit, theoretically you should have infinite life, but as I told you previously, this may not happen. So in this problem, what are we going to do? We are going to deal with the exact same problem, but we will assume that SE is 200 megapascal, SUT is a 350 megapascal, and we want to use only Goodman, okay? And we want to know what is the fatigue life. If the fraction factor is 0.9. Now, it's سؤال غريب صح؟ فجأة جاء وقال لك what is fatigue life? What is it? Now, I'm gonna tell you this, listen to me carefully. For the final exam, okay? If I bring you this question in the final, I can bring it into two ways. One way, 80% of the class will solve it. كلكم حتاخذوا في المارك. The other way, same question, I will change a little bit. I will change this or this. And then 80% of you will get 0. Is this scary enough for you to pay attention now? Now, what is it? Oh, I'm going to show you. Ya shabab, when we solved the problem, okay, what did we get? I'm going to tell you what did we get. We got, and I'm going to go back to the slide. Okay, here. We got sigma A prime equals to 145.5 megapascal. This is from von Mises. We did it in the previous lecture. And sigma M prime, we got it equals to 178.4 megapascal. We can't change it. Number one, we have an amplitude. Number two, we have a mean, which is 178, and it is positive. So we need to use Goodman, Gerber, Azmi elliptic, because it's a positive mean. There is no question about it. Now, in this question, هو قال لك أبقى Goodman بس. Now, السؤال كالتالي. You see, if you use Goodman, okay, look what will happen. You will say that NF, Goodman, says that NF equals to 1 divided by the amplitude 145.5 divided by SE. SE in this problem was given as 200, was very kind of question. And then a plus the amplitude, the mean was 178.4 divided by the amplitude, which was given to me as 350. Now, if I solve this, I get 0.808. Now, when I get the factor of safety less than 1, what does it mean? I just told you. It means you have a finite life. That's why the question is asking you, what is the fatigue life? What is it? How many cycles? So now this is the question. The part below is a lecture. It's a very little tiny equation. احنا يا شباب نعرف بأنه equation for fatigue life, if you remember it, N, I'm gonna write this in blue, okay? So N fatigue life equals to A multiplied by what? No, I did this wrong, so sorry. We said that sigma reverse equals to A N to the power B. Then N is equal to sigma reversed, completely reversed, divided by A to the power 1 over B. Now, from maybe the second lecture, we told you go and put REV, يعني معناها completely reversed. صح? Now the problem is this. My problem has a factor of safety which is less than 1. So I should determine fatigue life, but the equation مو بكيفي. The equation says you should put a completely reversed stress. هنا يا شباب, is this a completely reversed stress? Come on. Send me the last bullet. Is this a completely reversed stress?
No.
No,
That's
do you all agree يا شباب? Thank you يا حسن. Do you all agree? No, is this a completely reversed stress?
No, doctor, the mean should be 0, right?
Exactly. كويس, okay. This is not a complete reverse. Why? Because the mean is not 0. Can negative, positive, it doesn't matter. If the mean is not 0, then this is not reverse stress. What does this mean? I cannot use this equation. So how can I use it? Did we teach you any other equation, يا أخوان, to find a completely reverse stress? No, we didn't. So in this last lecture of the chapter, what are we going to do? We are going to give you 2 equations, okay? Which are one based on Goodman, the other one based on Gerber. And their job is to find sigma reversed, if you have both amplitude and mean. You understand? So how is that equation? Sigma REV is equal to what? Sigma A divided by 1 minus sigma mean divided by SUT. This one is called the Goodman correction or conversion. We convert a state which is amplitude and mean into one single amplitude only. The result here is going to be a completely reversed amplitude. You understand? Very nice trick. And then we have another equation by Gerber. Gerber said the reversed amplitude from sigma A and sigma M is equal to sigma A divided by 1, and then you put sigma mean divided by SUT, and then you square the ratio. A little difference. Now, in our problem, we were asked to use Goodman. So what are we going to do? Do you need anything, ya Faris?
Yes, is it compression, sigma U compression or tensile?
No. Tension. Remember, Goodman.
Because it's written C.
Did I? Oh, no.
I think.
T. It is T. Remember, there is no Gerber, no Goodman, no Söderberg, nothing, no Azmi elliptic for negative mean. Gerber or Goodman, those names should never come whenever there is a negative mean. Never. Do you understand? Okay, ya akhwan. Good. Now, So let's go back to the equation then and say, okay, that sigma REV is equal to 145.5 divided by 1 minus 178.4 divided by the yield, which is 350. And then this is equals to 296.77 megapascal. Now, what is the claim of Gerber here or Goodman? This is based on Goodman because the problem, إذا قال لك استخدم NF Goodman, then you should use the correction factor or the conversion factor for Goodman. You don't mix them up. So what is the story here? Goodman now tells you that the new loading is a completely reversed loading with amplitude minus 296.77 and plus 296.7. Very beautiful. The old one, the original one, was like this. There was a mean of 178.4, and in the mean there was an amplitude of 145.5. Then what did we do? Using that little tiny equation, we converted it into a simple zero mean state. Now, if we do this, all what we need to do is to find A. A is equals to F SUT squared divided by SE. B is equal to minus the 1/3, the log for F SUT divided by SE. You find these, and then you substitute the equation. But when you substitute, look, you put the new reversed loading, which is 296.77 divided by A to the power 1 over B. And then what did you get? You get 2,476 cycles. That's it. Now, you may ask me now a question. What is the thing that you will do to make 80% of the student get 0? What is it? Very simple. What I'm going to do, I will increase this more. I will increase this one more. Make them up. When they are up, the material strength increases, and then you will get a factor of safety of 1.2, 1.3. And when I ask students what is the fatigue life, what are they going to do? They will go, they will use this equation. They will use Gerber equation. They will do exactly the same step. And what is going to be the result? The result, إنه الرقم هذا حيطلع like 10 to the power 100, 10 to the power 9, 20. Huge life. Yes, ya Ali.
No, nothing, Victor.
Okay. But what is wrong with a huge life? The wrong matter here is that all of these equations were built between 1,000 and 1 million. If you use them to solve the life beyond 1 million, it's wrong. You get a huge number, yes, but it means that you don't understand anything. The life, the answer, by the way, is infinite. Unlimited. At least based on the theory. And this is the problem. This is why some of you did not know to answer. What does failure mean in yielding? What does NF mean in fatigue? You understand? So when you get NF greater than 1, don't calculate life. Just say that the life is infinite. Theoretically infinite, to be more precise. And as far as your book is concerned, you are allowed to say this. Tell me it is infinite life, أقول لك صح. But if you are a research student, I will tell you no. Now, if the factor of safety is less than 1, it means you have finite life. There is a lot of calculation to be done. You need to tell me, what is this life? Don't assume no, oh, NF is less than 1, so failure. No, not failure. Who said that? 2,476 cycle might last for a year. 1 full year, why not? Maybe. So that's the thing that I want you to remember. Now, yes?
Sorry. The finite life, that means from 1,000 to 1 million, like we took in the early chapter.
Exactly, yes. Yes.
So,
yes, and whenever you solve, listen, Shabab, whenever you solve this equation, yes, Ya Faris.
Continue, Doctor.
Whenever you solve this equation, automatically in your head, قبل ما الكالكوليتر تطلع الرقم, you should expect 1,000 to 1,000,000 in between.
Yeah, that's my point.
If you don't get that, there is something wrong. Something is wrong. Got it, Ya Shabab? Now, the remaining slides, okay, from 104 to 112 is a summary, which is called the roadmap for important design equation for stress life method. Everything we discussed nicely been put in 2 pages, maybe in the textbook with 2-sided. So I summarized them for you here, all of them, which is starting by calculating the rotating bending endurance limit, and then Ka, all the table, all the equations are summarized here. Very beautiful summary. So you may want to use this in the final exam, even in the design, because you don't need to jump from one page to another. You can go to the end of the chapter and you will see this roadmap, how to calculate the stress concentration factor. Look, all of the criteria for positive mean stress. And then look, this is the Goodman and Gerber correction for calculating the fatigue life, as well as for combined loading. Now, Ya Akhwan, I need to move to a few slides. I'm going to go over them a little bit quickly. The purpose of these slides is to give you some side notes. There were some questions which were asked I could not answer. And sometimes there was some hint. I told you because of time, I will not be able to answer you. I will get back to you. So this is me making up my promise. Now, for the temperature factor, we talked about it a little bit quickly, Ya Shabab. So as you see, this example, which is in your textbook, shows you the 2 methods, which, by the way, I explained to you verbally, okay, but we did not talk about them. So in this problem, what does it say? It says that there is a temperature effect in the fatigue life. I mean, in the endurance limit, you perform a test or you perform an operation for the machine under a higher temperature. So you want to know what are the consequences. So basically, we told you there are 2 methods. The first one is to use the equation, which is KD, okay? Now, the problem says that you have been using this at a temperature of 450 Fahrenheit. And what did I tell you? I told you that this equation, which I just boxed here, has a T factor in it, which you need to apply the temperature, look, and it has to be in Fahrenheit. If you do that, what do you get? You will get a factor of the KD, which turns out to be 1.007. Now, one of you might ask, كيف انت قلت انه KD in general, not KD, KA, KB, KC, KD, KE, KF, usually they reduce the endurance limit, not improve it. So why here we have a number which seems like it will increase the endurance limit by a little bit. With temperature, Shabab, we all know that steel, at certain temperature, there is relaxation in for example, if there are residual stresses, grain boundaries, might diffuse carbon into the grain or the opposite. And these things at temperature, for example, 300, 400 for a period of time, it may make your material a little bit stronger. And that's why you have a factor which is a little bit more than 1, okay? Now, so in here, what did we do? We take the endurance limit at room temperature, which is 70 Fahrenheit, and we multiply it by KD, and this is how we find the endurance limit. Now, the other way, ya shabab, is to get it from the table. That table, there was a table given to us, which has ST divided by SRT. And that table will give you ratios. So what is this table? This table, ya shabab, طبعا, the table, ya shabab, is given at certain temperatures. So if you have the ratio ST divided by SRT, for example, at temperature 20 and then 50, and you want to find the temperature at 40 or 35, what should you do? You can interpolate. So this one is the interpolation to get this ratio for the 450 Fahrenheit. Now, what does this mean? This factor, ST over SRT, what does it mean exactly? It means, ya shabab, that this is the ratio between the room temperature ultimate strength and the ultimate strength at the temperature that you are operating at. So by knowing the factor and by going to the back of the book, you can find the ultimate strength at room temperature, صح? Which is SRT, room temperature. And now look, you can go and find the ultimate strength, okay, which is the at room temperature at 450 by multiplying the factor, okay, by SUT, and at 70 degrees, which is the room temperature in Fahrenheit. And then you get the new, what? The new ultimate strength. Now, when you get the ultimate strength, this strength now, the ultimate strength is at 450 Fahrenheit. So what do? You use this one and you multiply it by 0.5. There is no need to multiply by KD, خلاص. Why? انت امامك خيارين وهذا اللي قلته في الماضي. الخيار الاول انك تستخدم ultimate strength which is at the high temperature that you are using, or you keep the ultimate strength at room temperature and you multiply it by KD. You have the two choices, and this is the example to show you these two choices. Another point that was asked by one of you is, what does this mean? Okay, what does this mean? I want to tell you that if you recall the question, that this line over here, what is it representing, ya shabab? This line represent, if you hit a point here, look, this is 1 point for 10,000 cycle curve. This is the intersection point for 100,000, and this one is the intersection point for 1 million. Okay, now احنا ايش قلنا؟ قلنا if you have any point on the curve right here, then what should you do? You should draw a perpendicular line like this and a perpendicular line like this, and then what happened? You can find sigma mean, you can find sigma A, correct? But what does it mean to have a point on the curve? What are you gonna do?
That means there is a life.
I understand. I mean, sorry, and I asked the wrong question. What does it mean to have a point on the axis? يعني مثلا, and let me show you. If we have x coordinate and y coordinate, if we have a point here, then this is the x1 coordinate, this is y1. But if you have a y on a point in the y coordinate, what does it mean? And no, the value of x is 0. And the value of y is the magnitude of that length. Same thing, if you have a point here, it means y is 0 and x has a value. So if you are here in this point, this is the point when the mean stress is only applied, which means it's like a tension loading. There is no amplitude. And in this side, what happened? You have only what? Only amplitude. There is no mean. طيب, if we have only amplitude, there is no mean, what is the R ratio? Is equals to -1. صح ولا لا? So this value over here belong to R ratio equals to -1. Now, R ratio equals to sigma minimum divided by sigma maximum. So if sigma minimum and sigma maximum are the same, then you should get R equals to -1. Do you want to see it? Let me show it to you. Look, if I take this point over here, and then I go down, what is the maximum? What is the minimum? -90, right? I have what here is 90, correct? -90 over 90 is -1. That's it. What is A? A equals to sigma A, sorry, A equals to sigma A divided by sigma mean. And if the mean stress is equals to 0, you get this as infinity. Sorry, ya shabab, this is gonna explode. You get as infinity. And that's why this point here, which belongs to this curve, is indicated as R equals to -1 and A as infinity. Understood, shabab? Now, what you should know is that if you go up over here, this is 120. This one as a value is going to be 140. This one, 160. And this one, 180. You got that? You continue the same scale. But this line belong to our ratio of -1, okay? Now, what was the other thing? KB, ya shabab. For KB, ya akhwan, we have to be careful, okay? KB, if you have bending, okay, what is going to be KB? You use this equation. Where is it? No. I brought this problem just to warn you about something. Now, what happened? KB, ya shabab, if you have this problem, if you remember, this problem was a cantilevered beam, which was rectangular, okay? And what did we say? We say if you have a rectangular beam, you should use for KB an equivalent diameter, which is this equation, which is equal to 0.808 square root of BH. This is B, this is H. Now, some student asked, and they said, but we have another equation, which is DE equals to 0.37, what? By the diameter. And they said this one is for non-rotating. You understand? Now, this one is also not rotating. It is fixed. So why did we use this one? We did not use this one. One reason. I know this question might be easy for some of you, but yeah, some students get confused. This one is for non-rotating round, which means if you have a round and it is not rotating and there is a cyclic loading on it, then you should use this equation. But if you have a rectangular geometry, whether it is rotating or rotating, you should use this. Do you understand? Okay. Now, also, I want to just tell you about something we did not speak about from the beginning, which is this. In this problem, if you remember, when we calculated the in this problem, ya shabab, when we calculated the maximum stress to find, the yielding, what did we do? We calculated the stress in here by dividing the force over this area, and then we compare that with yielding. So some of you might ask, why didn't we multiply sigma, which is equals to F over A? Why didn't we multiply it by KT? I'm talking about yielding, huh? For yielding. For fatigue, what did we do? We used the KF in here and we multiply it by the stress amplitude. But why didn't we take the maximum stress, whether it is minimum or the maximum value or the minimum value, and we multiply it by KT, اللي هو geometric stress concentration factor? There is one reason, ya shabab. You did this in civil engineering, and in general with civil engineering you were dealing with the mechanics of solid. We don't necessarily know if you used a brittle material, a ductile material, but as far as we go in this course in mechanical engineering, and exactly for this textbook, for this course, everything is about steel and aluminum. دائما نتكلم عن metals. What happened? We don't apply stress concentration factor for monotonic static loading. We don't. The reason why is because we think, since we design based on yielding, then if this part did not yield, then this part, which might have higher stress because of KT, will not cause failure. Why? Because most metals we used for machinery, they have stress hardening, which means once you exceed the yield stress, the stress become higher and higher, and it become harder to to deform the material. So here, yes, the stress might go higher than yielding, but it is not gonna go up high to break the material. This is what we think, since we are designing based on yielding. Do you understand? So in general, we think that hardening of the material is going to support the stress concentration region, and it's not gonna let it fail. But definitely, if you apply your design based on ultimate or fracture, you should consider the stress concentration. That's a different matter. Okay. Now, بالنسبة يا شباب للتورجن، أنا قلت لكم بأنه I explained to you the torsion, but I am pretty sure many of you will be confused if you have a condition where only pure torsion is applied. So if you have only pure torsion applied, let's say there is a shaft, okay, and then you apply cyclic torsion. يعني مسكته كذا and then you cycle it, cyclic torsion only, no bending, no axial loading. Then for this material has SUT, صح ولا لا? Then what should you do? If this is cyclic, then you can find SE prime using SUT. If it is less than 1,400 megapascal, then SUT is, SE prime equals to 0.5 SUT. Then what should you do? You should multiply KC as 0.59. This is what I told you. in order to find SE. Understood? So you use SUT, not for shear. You don't use the shear one. You just use SUT for tension, but then you apply this one for KC. Now, what about KA? What about KA? Ya shabab. KA equal to a factor multiplied by SUT to the power B. أيضا, you can use SUT for tension to find A and B. Why? Because KC is going to take care of the correction for you. You did not use SU for shear. You did not use for shear. You used for tension. And again, 0.59 is going to correct it for you. What about KB? KB, in the equation for KB, it says that if you are applying bending or torsion, or in reality, any of these. So if you have a multi-axial loading, and in multi-axial loading, you will have, for example, axial, torsional, and bending, then you should use KB based on the diameter. ما في شيء. تروح تشوف الdiameter, and then you find the equation. There's nothing changed here. Now, how about Q for shear? Q for shear, ya shabab, is given to you the curve. This is R, and this is a Q, and the curve is given to you based on SUT. خلاص ما يحتاج تغير. Use SUT for the material to find the Q for shear. هو given to you based on ultimate strength for tension. If it was given to you based on the ultimate strength for torsion, then it's okay. But no, it isn't. Now, the idea is this. What you need to be worried about is A and B in the fatigue life equation. This is where you should use SU, the ultimate strength for shear, which is, as we said, you should multiply by 0.67 SUT. Same thing with B in the fatigue life equation, which is F SUT squared divided by SA. So you should use not SUT, you should use SSU. How do you find it? You multiply it by 0.67. And the same for B. If you have yielding, like in Söderberg or Azmi elliptic, you should use the yield strength, the yield correction for von Mises, which is 0.577. KB in multi-axial loading, ya shabab, as far as there is tension or torsion, I mean there is bending or torsion, you should just use it regularly. You don't need to do anything, okay? And that's it. I was supposed to solve, ya shabab, the midterm, but since I couldn't, I will do this next class and then we will start chapter 7 right away. For now, we concluded chapter 6, and I just want to ask you to turn on your webcam so I can take your attendance, please. And then you are free to leave, okay? When I call your name, you can leave right away since we have almost 1 minute only left, so I am sorry for the delay. Okay, Faisal? Faisal?
Yes.
Where are you?
Here.
Oh, okay, I see you. Okay, Yusuf?
Here, present.
Hamad?
Yes.
Hamad?
Yes.
Ali?
Yes. Yes, here.
Yusuf? Majid?
Yes.
Ali?
Yes.
No, Al-Ali, Hussein.
Yes.
Okay, Muhammad?
Yes.
Okay, Hassan Ayyash, I think your Hassan
Yes.
was here, right? Yeah. Okay, Mubarak? Ahmed?
موجود يا دكتور.
علي؟
موجود دكتور.
معجب؟
Yes, دكتور.
سلطان الحربي؟
موجود يا دكتور.
عبد الله؟ حجاب؟
موجود.
سلطان،
Yes.
روشان، عبد الرحمن،
موجود دكتور.
خالد العتيبي،
موجود دكتور.
عبد الله العوفي،
موجود.
فارس،
موجود يا دكتور.
ثابت.
حاضر دكتور.
اوكي، رمضان،
موجود دكتور.
هاشم،
موجود.
ماجد،
موجود.
محمد.
موجود يا دكتور.
اوكي، احمد، سلطان. I think you're
موجود
here.
دكتور.
مشعل،
موجود دكتور.
وليد، وليد، بارشيد،
موجود دكتور.
عبد الله،
موجود دكتور.
and احمد.
موجود دكتور.
اوكي، thank you so much يا شباب.
دكتور
يس.
عندي سؤال بس بسيط دكتور، بدل ما اجيك الافصار هل اقدر اسالك الحين؟
يس يو كان، تفضل.
دكتور بخصوص